Welcome to section 8.3, interval estimation. In this section, we explore how to use sample data to make reliable guesses or estimates about unknown population parameters. Imagine trying to estimate the average number of hours college students spend gaming, or the percentage who prefer online classes. With a large enough random sample, statistics gives us the tools to make solid, evidence-based predictions. By the end of this lesson, you'll know how to construct and interpret confidence intervals for both population means and proportions, even when you don't know the full population. When we estimate something like how many Fortnite players log on daily, or what proportion of students prefer online classes, we don't usually get the exact number for the whole population. That's where confidence intervals come in. They give us a range that we can be reasonably sure includes the true value. Think of it like aiming a bow. You rarely hit the bullseye, but you want to land close. A well-constructed confidence interval is your aiming zone. So a confidence interval gives us a range of values that we believe with a certain level of confidence contains the true population parameter. For example, instead of saying we think the average is 2.6 hours, we might say we're 95% confident that the true average is between 2.3 and 2.9 hours. This accounts for sampling variability. As I just said, it's like shooting arrows at a target with a certain degree of accuracy. Some shots may be off, but most will hit close to that bullseye. Let's say you pull your dorm and find that 60% of residents prefer Taco Tuesday over Wing Wednesday. That 60% is your point estimate, but you're not claiming it's exact. You add a margin of error and say, I'm 95% confident the real number is between 55% and 65%. That range is your confidence interval, and the confidence level tells others how much faith to place in it. The general formula for a confidence interval is the estimate plus or minus the margin of error. That margin of error is determined by a z-score based on your confidence level, like 95% or 99%, and the standard error, which reflects variability in the estimate. So if our estimate is 0.60 with a margin of error of 0.05, our interval would be 0, whoops, forgot to turn on the pen. Our interval would be 0.60 plus or minus that 0.05, the margin of error value. So if I subtract it, that's 0.55. And if I add it, it's 0.65. This tells us if we repeated the survey many times, about 95% of the intervals we'd create would contain the true population proportion. So this is your go-to formula. The point estimate plus or minus z times the standard error. It's like building a fence around your best guess. The z value depends on how confident you want to be. So we would use 1.96 for 95% confident, 2.58 for 99% confident, and so on. Let's say you want to estimate the average time Fortnite players spend per session. You sample 50 players, and the average is 2.8 hours. Using the formula and plugging in S equals 0.6, N equals 50, we compute the margin of error, and then we create the interval. So our X bar is 2.8. So we would have X bar is 2.8. The Z alpha, because it's 95%, we just saw from the last screen, that's 1.96. Times S is 0.6 over the square root of N is 50. So I'm going to calculate this portion here, which is my margin of error. And then I'm going to subtract that from 2.8 and add it to 2.8. That'll give me a range of values on the number line, right? With 2.8 at the center and 2.63 on the left and 2.97. So we are 95% confident that this interval between 2.63 and 2.97 contains the true value. This helps Epic Games know how long to keep servers ready during peak hours. This example shows how to build a confidence interval for a proportion. We take the sample proportion. In this case, it's going to be 122 over 200, or 0.61, 61% of students who binge watch, and calculate the standard error. So we use our formula for the standard error. We're using the p hat, q hat. So 0.61 times 1 minus 0.61 over in the 200. Take the square root of the whole thing, we get 0.34. So our confidence interval is our estimate, 0.61, p hat, plus or minus 90% corresponds to a 1.645z, times the standard error we just found, 0.34. So 0.554 to 0.666. With 90% confidence, we estimate the real proportion is between 55.4% and 66.6%. That's solid information for streamers deciding what to license on campus. A 95% interval doesn't guarantee the true value is inside this interval. But if we did the same survey 100 times, 95 of the resulting intervals would contain the truth. If you want more confidence, you can widen your net, but it gets less precise. Want both confidence and precision? Survey more people. 3 main things affect how wide a confidence interval is. First, the sample size, n. Larger samples give more precise estimates, making the interval narrower. Second, variability in the data, the sigma or the s, the standard deviation. More variability means a wider interval. And third, the confidence level. A 99% confidence interval is wider than a 95% interval because we want to be more sure. Think of it like fishing. The more data fish you catch, the better your sense of what's really in the lake, and the smaller your margin of error. In summary, point estimates give us a best guess of population values. Confidence intervals give us a range of plausible values based on sample data. Larger samples, less variability, and lower confidence levels result in narrower intervals. These tools let us use a small snapshot of data to draw meaningful conclusions about larger populations. Confidence intervals help us move from a single guess to a smart range. Whether we're estimating how long players spend in Elden Ring or what proportion of students prefer online classes, confidence intervals add credibility to our estimates. Just remember, no statistic stands alone. Always consider how confident you are and how precise your interval really is.